In this video, we are going to talk about radical addition reactions. We're all very familiar with the electrophilic addition reaction that is happening in alkenes and alkynes, where we have to use the Markovnikov's rule to predict the product. According to Markovnikov's rule, the electrophile is going to get added to the carbon, which has the most number of hydrogens across the double bond or triple bond. So here in this case, when you add HBr, the H is going to be your electrophile and it's going to get added to the carbon which has the most number of hydrogens, right? And the nucleophile is going to go to the other carbon. The Br is going to go to the other carbon, right? So the product here in this case would be 2-bromobutane. This is the product that we'll be getting for this particular reaction. Now let's say that we want to prepare 1-bromobutane. What is the best way to synthesize 1-bromobutane with the same HBr? So here in this case, we have to use peroxide. So this would be a radical addition reaction where anti-Markovnikov's rule will be followed. Okay, so the product here would be 1-bromobutane. And in order to understand the mechanism for this reaction, we have to first learn about peroxides. What are peroxides and how are these formed? Peroxides are explosive compounds. And these explosive peroxides are formed when ethers react with oxygen in the presence of air. Now let's look into the mechanism for the formation of peroxide. In the first step, a chain initiating radical is going to go remove the alpha hydrogen from the ether molecule. Now look into this. This is your ether molecule, and if you consider this is your functional group, okay, this carbon right here is the alpha carbon, and the hydrogen that is attached to that carbon is the alpha hydrogen, right? So the chain initiating radical is going to remove this hydrogen first. So let's draw the steps here. So it's trying to form a bond between hydrogen and Y, where this bond is going to cleave and it's going to come together and it's going to create a new radical. So here is the new radical that is created. Okay, and this is called as the initiation step, because a new radical is created. The next step, this newly formed radical is going to react with oxygen to form the peroxide radical. So this is going to be a propagation step. And this is going to be a first propagation step where this radical which is created in the initiation step is going to react with oxygen to form a peroxide radical. Okay, so again, there is going to be a new bond that's created between oxygen and carbon. Okay, and it's going to form the peroxide radical. So this is our peroxide radical. And in the next step, the next propagation step, this peroxide radical is going to react with another molecule of ether and removes an alpha hydrogen from that molecule to give the peroxide and also the radical which has been created in the initiation steps. So this peroxide radical will react with another molecule of the same ether that we started with, removing the alpha hydrogen. So again, this is your alpha hydrogen, and it will basically try to form a bond between these two, between oxygen and hydrogen, and the electrons in here is going to go onto the carbon. Thereby forming the peroxide and the radical which is generated in the first step. This is peroxide, where you can see that there is a single bond between the two oxygens, and this bond right here is relatively weak and it can be easily cleaved homolytically, where one electron is going to go on to each one of those oxygen atoms, thereby creating the peroxide radical. And this peroxide radical is going to create another new radical, and the reaction goes on and on, creating the explosive reaction. Okay, and that is the reason why ethers always contain a stabilizer which is going to trap the chain initiators. Okay. So basically, the peroxides are radical chain initiators. Here is a mechanism for the radical addition of HBr to an alkene molecule. And remember, for this reaction to happen, you need to have peroxide because that's going to be a radical chain initiator. And we also need to have light or heat for the reaction to happen. Okay. In the first place, the peroxide is going to undergo homolytic cleavage to give two alkoxy radicals. Okay. So where this bond right here is going to break homolytically and it's going to result in two alkoxy radicals. Once the alkoxy radical is created, it's going to react with a molecule of HBr to give the bromine radical, and both of these steps are initiation because we need the radicals in order to proceed with the propagation steps. Okay, so this alkoxy radical is going to react with HBr to give the alcohol and the bromine radical. So basically, these electrons are going to come in here and it's going to result in the formation of alcohol and bromine radical. Okay, once this bromine radical has been created, it is now going to react with the alkene molecule to give the alkyl radicals. Now it has two chances. It can create a primary radical or it can create a secondary radical. Let's say if the bromine radical gets added to this carbon right here, okay, then it is going to result in the formation of a secondary radical. If the bromine radical is going to get added to this carbon, then it's going to result in the formation of a primary radical. Now, which one of this is more feasible, or which one of this is going to be more stable? Yes, of course, it is going to be the secondary radical that's going to be more stable. So we are going to proceed the reaction with that. So the bromine radical is going to react with our alkene. So here is our alkene. And it's going to react with a bromine radical. Okay. So where the pi bond is going to break and it's trying to form a bond between carbon and bromine radical, and this electron is going to go on to the carbon. Okay, now this is going to generate an alkyl radical, a secondary alkyl radical. Okay, this is the propagation. This is the first step in the propagation, and this step will be followed by the by another propagation step wherein this alkyl radical, this is our alkyl radical, this alkyl radical is going to react with HBr, abstracting the hydrogen to form the actual product that we want. So this is the product that we'll be needing for this reaction, right? So this alkyl radical will react with HBr, removing the hydrogen from this HBr. And it's going to also create the bromine radical. So this is the product that is formed. This is the actual product that we need for this reaction. And for the termination, we can have two bromine radical coming together to form the bromine molecule, right? Or we can have one alkyl radical and one bromine radical to form the dibromo compound. So remember, these electrons are going to come in here to form the bond between carbon and bromine. Or you can have two alkyl radicals coming together to form a bond between carbon and carbon, right? So So it's going to form a bond between carbon and carbon. Now here is a question. Will there be carbocation rearrangements happening in the radical addition of HBr to an alkene? The answer is no, right? Why? Because there is no carbocation intermediate. Because there is no carbocation intermediate, there is no possibility for carbocation rearrangement. If we want to write the product for this reaction, then we have to just keep the carbon skeleton as it is and write the product. So where the bromine is going to go to this carbon, right? And the hydrogen is going to go onto the carbon, and this is done at the expense of the pi bond. Okay, so the product here would be this, where you can see that the carbon skeleton has remained unchanged. So you have exactly the same carbon skeleton in both of these compounds. There is no 1 to metal shift or 1 to hydride shift that is happening in this reaction. Peroxide effect occurs only with HBr addition. It does not happen with HCl or HI addition. Even if you're going to add peroxide, the product that you will be getting from here would be just similar to the one that you will be getting in an electrophilic addition reaction. Major product would be the Markovnikov's product. For an radical addition reaction, it would be anti-Markovnikov's product, right? So here in this case, there is still Markovnikov's product where the hydrogen is going to go to the carbon, which has the most number of hydrogens, and the Cl is going to go to the carbon, which has the least number of hydrogens. So the product here would be this, right? Even though you have peroxide in here, it is still going to do the electrophilic addition reaction and not the radical addition. Okay, similarly in here, the product would be where the hydrogen is going to go to the carbon, which has the most number of hydrogens. Okay, remember the hydrogen has gone to the carbon, which has the most number of hydrogens, and the iodine has gone to the other carbon. Okay, so there is only electrophilic addition reaction taking place when you have HCl and HI. There is no radical addition. Now, what is the reason why peroxide effect occurs only with HBr and not with HCl or HI? Now, the answer for this comes from the delta H values. So if you take a look into the both the propagation steps, we can see only for HBr, we have both of those steps to be exothermic. Whereas in the case of HCl and HI, there is at least one reaction which is endothermic, right? In order for the radical addition reaction to proceed successfully, we want both of those steps, propagation step and as well as the termination step, to be competing each other, right? So the termination step by default is going to be exothermic, right? Because there is no bond formation. And because at least there is one step which is endothermic in the HCl addition and the HI addition, this propagation step cannot compete with the termination step, and therefore it's not possible for us to get the radical addition product. There is only electrophilic addition happening in HCl and HI even though you add peroxide to it.